We're going to get started. Handouts are by the door if anybody didn't pick one up. My name is Charles Leiserson. I'll be lecturing this course this term, Introduction to Algorithms, with Eric Demain. So in addition, this is an SMA course, a Singapore-MIT Alliance course, which will be run in Singapore by David Hsu. And so all the lectures will be videotaped and made available on the web for the Singapore students, as well as for MIT students who choose to watch them on the web. If you have an issue of not wanting to be on the videotape, you should sit in the back row. Okay? Otherwise, you will be on it. There is a video recording policy, but it seems like they ran out. So if anybody wants to see it, people, if they could just sort of pass them around maybe a little bit, or once you've done reading it, or you can come up and I did secure one copy. Before we get into the content of the course, let's briefly go over the course information, because there's some administrative things that we sort of have to do. As you can see, this term we have a big staff. So take a look at the handout here. Including this term 6 TAs, which is 2 more TAs than we normally get for this course. So that means recitations will be particularly small. There is a World Wide Web page, and you should bookmark that and go there regularly, because that's where everything will be distributed. Email, you should not be emailing directly to the, even though we give you our email addresses, directly to the staff in general, to the individual members of the staff. You should email us generally, and the reason is you'll get much faster response. And also, for any communications, generally we like to monitor what the communications are, so it's helpful to have emails coming to everybody on the course staff. As I mentioned, we'll be doing distance learning this term. And so you can watch lectures online if you choose to do that. I would recommend for people who have the opportunity to watch, to come live. It's better live. You get to interact. There's an intangible that comes with having it live. In fact, in addition to the videos, I meet weekly with the Singapore students so that they have a live session as well. Prerequisites. The prerequisites for this course are 6042, which is Math for Computer Science, and 6001. You basically need discrete mathematics and probability, as well as programming experience to take this course successfully. People who do not have that background should not be in the class. We will be checking prerequisites. If you have any questions, please come to talk to us after class. Let's see, lectures are here. Okay, for SMA students, they have the videotapes, and they'll also be in, and they also will have a weekly meeting. Students must attend a 1-hour recitation session each week. There will be new material presented in the recitation. Unlike the lectures, they will not be online. Unlike the lectures, there will not be lecture notes distributed for the recitations in general. Okay, and yet there will be material there that is directly on the exams. And so every term we say, oh, when did you cover that? That was in recitation. You missed that one. So recitations are mandatory. And in particular also, let me just mention, your recitation instructor is the one who assigns your final grade. Okay, so we have a grades meeting and we keep everybody normal, but your recitation has the final say on your grade. Handouts. Handouts are available on the course webpage. We will not generally, except for this one first handout, we will not generally be bringing handouts to class. Textbook is this book, Introduction to Algorithms. Okay, MIT students can get it at any of the local bookstores, including the MIT Coop. There's also a new online service that provides textbooks. You can also get a discount if you buy it at the MIT Press bookstore. There's a coupon in the MIT student telephone directory for a discount on MIT Press books, and you can use that to purchase this book at a discount. Course website. This is the course website. It links to the Stellar website, which is where actually everything will be kept. SMA students have their own website. Some students find this course particularly challenging. So we will have extra help. We will post weekly office hours on the course website for the TAs. And then as an experiment this term, we're going to offer homework labs for this class. So what a homework lab is it's a place and a time you can go where other people in the course will go to do homework. And there will be typically 2 TAs who staff the lab. And so as you're working on your homework, you can get help from the TAs if you need it. And it's generally a place, and we're going to schedule those, and they'll be on the course calendar for where it is and when it is that they'll be held, but usually Sundays 2 to 4 p.m. Or else it'll be in some evening. I think the first one is an evening, right? Near to when the homework is due. Your best bet is try to do the homework in advance of the homework lab, but then if you want extra help, if you want to talk over your solutions with people, because as we'll talk about, problem sets you can solve in collaboration with other people in the class. Okay? In addition, there are several peer assistance programs, and those usually get also the Office of Minority Education has an assistance program, and those usually get booked up pretty quickly. So if you're interested in those, good idea to make an appointment to get there and get help soon. Okay, so the homework labs, I hope a lot of people will try that out. We've never done this. I don't know of any other course. Do other people know of courses at MIT that have done this? Yeah? 6011 did it. Okay, good. So, and was it successful in that class? Never went. Okay. Good. So we'll see. We'll see. Okay, if it's not paying off, then we'll just return to ordinary office hours for those TAs. But I think that for some students, I think that's a good opportunity. If you wish to be registered in this course, you must sign up on the course web page. So that's requirement 1, must be done today. You'll find it difficult to pass the course if you're not in the class. Okay? You should notify your TA if you decide to drop so that we can get you off and stop the mailings, stop the spam. Okay? You should register today before 7 p.m. And then we're going to email your recitation assignment to you before noon tomorrow. Okay? And if you don't receive this information by Thursday noon, please send us email, okay, saying to the course staff generally, not to me individually, saying that you didn't receive your recitation assignment. And so if you haven't received it by Thursday noon, you want to, I think you're going to try to send them out tonight, right, or at least by tomorrow morning. Yep. Okay. SMA students don't have to worry about this. Problem sets. We have 9 problem sets that we project will be assigned during the semester. A couple things about problem sets. Homeworks won't generally be accepted. If you are extenuating circumstances, you should make prior arrangements with your recitation instructor. In fact, almost all the administrative stuff, you shouldn't come to me to say, can I hand in something late? You should be talking to your recitation instructor. Okay. You can read the other things about the form. There are both, but let me just mention that there are exercises that should be solved but not handed in, as well to give you drill on the material. I highly recommend you doing the exercises. They both test your understanding of the material, and exercises have this way of finding themselves on quizzes. You're often asked to describe algorithms, and here's a little outline of what you can use to describe an algorithm. Okay, the grading policy is something that somehow I cover, and always every term there's at least a couple of students who pretend like I never showed them this. Okay, so if you skip problems, it has a nonlinear effect on your grade. Okay, nonlinear. Okay, so if you don't skip any problems, no effect on your grade. Okay. If you skip one problem, 100th of a letter grade. We can handle that. Okay? But 2 problems, it's a 10th. And as you see, by the time you've skipped like 5 letter grades, it's already a third of 5 problems. This is not problem sets, by the way. This is problems. Okay? You're down a third of a letter grade. Okay? And if you don't do 9 or more, so that's typically about 3 to 4 problem sets, okay, you don't pass the class. Okay, so I always have some students coming at the end of the year saying, oh, I didn't do any of my problems. Can you just pass me because I did okay on the exams? Answer, no. Okay, very simple answer because we've said it up front. Okay, so the problem sets are an integral part of the course. Collaboration policy. This is extremely important, so everybody pay attention. If you're asleep now, wake up. Okay? Yeah, like that's going to wake anybody up, right? Okay. So the goal of homework, Professor Domain's and my philosophy is that the goal of homework is to help you learn the material. And one way of helping to learn is not to just be stuck and unable to solve something, because then you're in no better shape when the exam rolls around. Okay, which is where we're actually evaluating you. Okay, so you're encouraged to collaborate, but there are some common sense things about collaboration. If you go and you collaborate to the extent that all you're doing is getting the information from somebody else, you're not learning the material. Okay, and you're not going to do well on the exams. So in our experience, students who collaborate generally do better than students who work alone. Okay? But you owe it to yourself, if you're going to work in a study group, to be prepared for your study group meeting. And specifically, you should spend a half an hour to 45 minutes on each problem before you go to your group, so that you're up to speed and you've tried out your ideas. Okay? And you may have solutions to some, you may be stuck on some other ones, but at least you've applied yourself to it. Okay? After 30 to 45 minutes, if you can't get the problem, just sitting there and banging your head against it makes no sense. Okay? It's not a productive use of your time. And I know most of you have issues with having time on your hands, right? Okay, like it's not there. Okay? So don't go banging your head against problems that are too hard, okay? Or where you don't understand what's going on or whatever. So that's when the study group can help out. And as I mentioned, we'll have homework labs, which will give you an opportunity to go and do that and coordinate with other students rather than necessarily having to form your own group. And the TAs will be there. So if your group is unable to solve the problem, then talk to other groups or ask your recitation instructor. Now that's how you go about solving them. Okay? Writing up the problem sets, however, is your individual responsibility and should be done alone. You don't write up your problems, solutions with other students. You write them up on your own, okay? And you should, on your problem sets, because this is an academic place, we understand that the source of academic information is very important. If you collaborated on solutions, you should write a list of the collaborators. Say, I worked with so-and-so on this solution, okay? It does not affect your grade. It's just a question of being scholarly. Okay? It is a violation of this policy to submit a problem solution that you cannot orally explain to a member of the course staff. So you say, oh, well, my write-up is similar to that other person's because, you know, I didn't copy them, you know. We may ask you to orally explain your solution. If you're unable, the presumption is, according to this policy, presumption is that you cheated. So do not write up stuff that you don't understand. Okay? So you should be able to write up the stuff that you understand how why you're putting down what you're putting down. If it isn't obvious, no collaboration whatsoever is permitted on exams. Exams is when we evaluate you, okay? And now we're not interested in evaluating other people, we're interested in evaluating you, okay? So no collaboration on exams. We will have a take-home exam for the second quiz. So you should look at the schedule. If there are problems with the schedule of that, we want to know early, okay? And we'll give you more details about the collaboration in the lecture on Monday, November 28th. Now, generally, the lectures here, okay, they're mandatory and that you have to know them, but I know that some people say, gee, 9:30 is kind of early, especially on a Monday, or whatever, okay? It can be kind of early to get up, okay? However, on Monday, November 28th, okay, you fail the exam if you do not show up to lecture on time. Okay, that one day, you must show up. Any questions about that? Okay, that one day, you must show up here. Okay, even if you've been watching them on the web. Okay? Generally, if you think you've transgressed, best is to come to us to talk about it. We can usually work something out. It's when we find somebody has transgressed from a third party or from obvious analyses that we do of homeworks. That's when things get messy. Okay, so if you think for some reason or other, you think, oh, I may have done something wrong, please come and talk to us. Okay, we were students once too, albeit many years ago. Okay, any questions? So this class has great material, fabulous material. Okay, and it's really fun, but you do have to work hard. Okay, so let's talk content. Okay, this is the topic of the first part of the course. The first part of the course is focused on analysis. The second part of the course is focused on design. Okay, before you can do design, you have to master a bunch of techniques for analyzing algorithms. Okay, and then you'll be in a position to design algorithms that you can analyze and which are efficient. So analysis of algorithm is the theoretical study of computer program performance and resource usage. And in particular focuses on performance. Okay, we're studying how to make things fast. Okay, in particular computer programs. We also will talk about other resources such as communication, such as memory, whether RAM memory or disk memory. Okay, so there are other resources that we may care about. Okay, but predominantly we focus on performance. Okay, so because this is a course about performance, I like to put things in perspective a little bit by starting out and asking, in programming, what's more important than performance? If you're in an engineering situation and writing code, okay, writing software, what's more important than performance? Correctness, good. Okay, what else? Simplicity can be very good, yep. Yeah. Maintainability. Okay, often much more important than performance. Cost. Okay, and what type of cost are you thinking?
Money.
No, but I mean cost of what?
Like hardware, computation. Well, I guess computation.
We're talking software here, right?
Okay.
So what type of cost do you have in mind?
I suppose it's a subset of resource usage.
Okay, yeah, so then you're sort of Okay, there are some costs that are involved when programming, like programmer time. Okay, so programmer time is another thing also that might be. Stability, okay, robustness of the software. Okay, does it break all the time? What else? Come on, we've got a bunch of engineers here. A lot of things. How about features? Features can be more important. Having a wider collection of features than your competitors. Functionality. Modularity. Okay, is it designed in a way where you can make changes in a local part of the code and you don't have to make changes across the code in order to affect a simple change in the functionality. Okay. Okay, there's one big one which is definitely, especially in the 90s, was like the big thing in computers. The big thing. Well, security, actually, good. I don't even have that down. Security is excellent, okay? That's actually been more in the 2000s, okay? Security has been far more important often than performance. Scalability has been important, although scalability in some sense is performance related. But yes, scalability is good. So what was the big breakthrough in the... I mean, why do people use Macintoshes rather than Windows, those people who are of that religion? User-friendliness. Wow, if you look at the number of cycles of computers that went into user-friendliness in the 90s, it grew from almost nothing to where it's now the vast part of the computation goes into user-friendly. So all those things are more important than performance. So this is a course on performance. Okay, so then you can say, okay, well, so why do we bother? Then why study algorithms and performance? Okay, if it's at the bottom of the heap. Almost always people would rather have these other things than performance. If you go off and you say to somebody, would I rather have performance or more user-friendliness? It's almost always, more important than performance. Why do we care then? Yeah?
You have to come back after 2 hours to get the right answer. That wasn't user-friendly.
That wasn't user-friendly. So sometimes performance is correlated with user-friendliness. Absolutely. Okay? Nothing is more frustrating than sitting there waiting, right? Okay, so that's a good reason. What are some other reasons why we...
Some applications real-time constraints.
Sometimes they have real-time constraints, so they don't actually work unless they perform adequately. Yep.
It's really hard to get exponential improvements in user-friendliness.
Hard to get we don't measure we don't usually quantify user-friendliness, so I'm not sure that's a... But I understand what you're saying, yeah. So we don't get, he says, don't get exponential performance improvements in user-friendliness. We often don't get that in performance either, by the way. Okay, sometimes we do, but... Okay, but that's good. Okay. So there's several reasons that I think are important. One is that often performance measures the line between the feasible and the infeasible. Okay, so we heard some of these things, for example, in real time, when there are real-time requirements, if it's not fast enough, it's simply not functional. Okay? Or if it uses too much memory, it's simply not going to work for you. Okay? And as a consequence, what you find is algorithms are on the cutting edge of entrepreneurship. If you're talking about just re-implementing stuff that people did 10 years ago, performance isn't that important at some level. But if you're talking about doing stuff that nobody's done before, one of the reasons often that they haven't done it is because it's too time consuming, it's too, things don't scale and so forth. So that's one reason, okay, is the feasible versus infeasible. Another thing is that algorithms give you a language for talking about program behavior. Okay, and that turns out to be is a language that has been pervasive through computer science, is that the theoretical language is what gets adopted by all the practitioners because it's a clean way of thinking about things. I think a good way I think about performance, and the reason it's on the bottom of the heap, is sort of like performance is like money. It's like currency. Okay, so you say, what good does a stack of $100 bills do for you? Okay, wouldn't you rather have food or water or shelter or whatever, and you're willing to pay those $100 bills for, if you have $100 bills, okay, for that commodity. Okay, even though water is far more important to your living. Okay, well, similarly, performance is what you use to pay for user friendliness. It's what you pay for security. And you hear people say, for example, that I want greater functionality. So people will program in Java, even though it's much slower than C, because it has, and they'll say, it cost me maybe a factor of 3 or something in performance to program in Java, but Java's worth it because it's got all these object-oriented features and so forth, exception mechanisms, and so on. And so people are willing to pay a factor of 3 in performance. So that's why you want performance, okay? Because you can use it to pay for these other things that you want, okay? And that's why, in some sense, it's on the bottom of the heap, okay? Because it's the universal thing that everybody is, that you quantify. Do you want to spend a factor of 2 on this, or spend a factor of 3 on security, etc.? Okay? And in addition, the lessons generalize to other resource measures, like communication, like memory, and so forth. And the last reason we study algorithms performance is it's tons of fun. Okay? Speed is always fun, right? Like, why do people, drive fast cars, race horses, whatever, okay? Rockets, etc. Why do we do that? Because speed is fun. Okay, ski, who likes to ski? I love to ski. Okay? I like going fast on those skis, okay? It's fun. Okay, hockey, fast sports, right? Okay, we all like the fast sports, okay? Not all of us. I mean, some people say, he's not talking to me. Okay. So, let's move on. So that's sort of a little bit of a notion as to why we study this, is that it does in some sense form a common basis for all these other things we care about. And so we want to understand, how can we generate money for ourselves in computation? Okay? So we're going to start out with a very simple problem. It's one of the oldest problems that has been studied in algorithms. It's the problem of sorting. Okay, and we're going to actually study this for several lectures. Okay, so we're going to, because sorting contains many algorithmic techniques. So the sorting problem is the following. We have a sequence A1, A2, up to AN of numbers as input. And our output is a permutation of those numbers. Okay, a permutation is a rearrangement of the numbers. Okay, every number appears exactly once in the rearrangement, such that, so I sometimes use a dollar sign to mean such that. Okay, such that A1 is less than or equal to A2 prime. Such that they're monotonically increasing in size. Okay, so take a bunch of numbers, put them in order. Okay? So here's an algorithm to do it. It's called insertion sort. And I'm going to write this algorithm in what we call pseudocode. So it's sort of a programming language, except it's got English in there often. Okay, and it's just a shorthand for writing, for being precise. Okay, so this sorts A from 1 to n. And here's the code for it. So this is what we call pseudocode. Okay. And if you don't understand the pseudocode, then you should ask questions about any of the notations. You'll start to get used to it as we go on. One thing is that in the pseudocode we use indentation, where in most languages they have some kind of begin-end delimiters, like curly braces or something in Java or C, for example. Okay, we just use indentation. The whole idea of the pseudocode is to try to get the algorithms as short as possible while still understanding what the individual steps are. Okay? In practice, there actually have been languages that use indentation as a means of showing the nesting of things. It's generally a bad idea because when you page from one, if things go over one page to another, for example, okay, you can't tell what level of nesting it is. Whereas with explicit braces, it's much easier to tell. So there are reasons why this is a bad notation, okay, if you were writing, if you were doing software engineering. But it's a good one for us because it just keeps things short, makes fewer things to write down. So this is insertion sort. Let's try to figure out a little bit what this does. Okay, so it basically takes an array A and at any point, the thing to understand is, so we're setting basically, we're running the outer loop from j is 2 to n, and the inner loop that starts at j minus 1 and then goes down until it's 0. Okay, so basically, so if we look at any point in the algorithm, we essentially are looking at some element here, j, a of j, the jth element. Okay, and what we do is essentially we pull a value out here that we call the key. Okay, and at this point, the important thing to understand is, and we'll talk more about this in recitation on Friday, is that there is an invariant that's being maintained by this loop each time through. And the invariant is that this part of the array is sorted. And the goal each time through the loop is to add 1 to the length of the things that are sorted. And the way we do that is we pull out the key, and then we just copy values up like this. We keep copying up, okay, until we find the place where this key goes, and then we insert it in that place. And that's why it's called insertion sort. Okay? So we just sort of move the things, copy the things up until we find where it goes, and then we put it into place. And then now we have that from A from 1 to j is sorted, and now we can work on j plus 1. Okay? So let's give an example of that. So imagine we're doing 8, 2, 4, 9, 3, 6. So we start out with 2, j equals 2, and we figure out that we want to insert it there. So now we have 2, 8, 4, 9, 3, 6. Okay? Then we look at the 4, and we say, oh, well, that goes over here. So we get 2, 4, 8, 9, 3, 6. Okay, after the second iteration of the outer loop. Then we look at 9, and we discover immediately it just goes right there. Very little work to do on that step. Okay, so we have exactly the same thing output after that iteration. Then we look at the 3. That's going to be inserted over there. 2, 3, 4, 8, 9, 6. And finally, we look at the 6. That goes in there. 2, 3, 4, 6, 8, 9. And at that point, we're done. Okay? Question?
Maybe I'm just confused, but should that be while I is greater than or equal to 0? Oh,
The array here starts at 1, yes. Okay? A 1 to n. Okay? Okay. So this is the insertion sort algorithm, and it's the first algorithm that we're going to analyze. Okay? We're going to pull out some tools that we have from our math background to help to analyze it. So first of all, let's take a look at the issue of running time. Okay? So the running time of this algorithm depends on a lot of things. Okay? So one thing it depends on is the input itself. Okay? So for example, if the input is already sorted, okay, then insertion sort has very little work to do. Okay? Because every time through it's going to be like this case. Doesn't have to shuffle too many guys over because they're already in place. Okay? Whereas, in some sense, what's the worst case for insertion sort? Yeah, if it's reverse sorted, then it's going to have to do a lot of work. Because you're going to have to shuffle everything over on each step, okay, of the outer loop. In addition to the actual input, it depends, of course, on the input size. So here, for example, we did 6 elements. It's going to take longer if we, for example, do 6 times 10 to the 9th elements. Okay? So if we're sorting a lot more stuff, it's going to take us a lot longer. So typically the way we handle that is we're going to parameterize things in the input size. So we're going to talk about time as a function of the size of things that we are sorting. So we can look at what is the behavior of that. Okay? And the last thing I want to say about running time is generally we want upper bounds on the running time. We want to know that the time is no more than a certain amount. And the reason is because that represents a guarantee to the user. Okay? So if I say it's not going to run, for example, if I tell you here's a program and it won't run more than 3 seconds, okay, that gives you real information about how you could use it, for example, in a real-time setting. Okay? Whereas if I said here's a program and, you know, goes at least 3 seconds, you don't know if it's going to go, you know, for 3 years. Doesn't give you that much guarantee if you're a user of it. So generally we want upper bounds because it represents a guarantee to the user. So there are different kinds of analyses that people do. The one we're mostly going to focus on is what's called worst case analysis. Okay? And this is what we do usually, where we define T of n to be the maximum time on any input of size n. Okay? So it's the maximum input, the maximum it could possibly cost us on an input of size n. Okay? So what that does is, if you look at the fact that sometimes the inputs are better and sometimes they're worse, we're looking at the worst case of those, because that's the way we're going to be able to make a guarantee. It always does something, rather than just sometimes does something. Okay? So we're looking at the maximum. Notice that if I didn't have maximum, then t of n in some sense is a relation, not a function. Because the time on an input of size n, well, it depends upon which input of size n. I could have many different times. But by putting the maximum at it, it turns that relation into a function, because there's only one maximum time that it will take. Okay? Sometimes we'll talk about average case. So sometimes we'll do this. Here, t of n is then the expected time. Over all inputs of size n. Okay? So it's the expected time. Now, if I talk about expected time, what else do I need to say here? What does that mean, expected time? I'm sorry? Raise your hand so I can see who's... Expected inputs. What does that mean, expected inputs?
So you expect the algorithm will run for a certain time, and so you're assuming that you'll receive a certain type of input.
Okay, I need more math. What do I mean by expected time here? Math. Over here.
You have to take the time of every input and then average it.
You have to take the time of every input and then average them. Okay. That's kind of what we mean by expected time. Good. Not quite. Okay. What you say is completely correct, except it's not enough. Not quite enough. Yeah. It's the time of every input times the probability that it'll be that input, which is a way of taking a weighted average. Exactly right. So how do I know what the probability of every input is? How do I know what the probability of a particular input occurs is? In a given situation. I don't. Okay, I have to make an assumption. What's that assumption called? What kind of assumption do I have to make? I need an assumption of the statistical distribution, okay, of inputs. Otherwise, expected time doesn't mean anything, because I don't know what the probability of something is. In order to do probability, you need some assumptions. Okay? You've got to state those assumptions clearly. So one of the most common assumptions is that all inputs are equally likely. That's called the uniform distribution. Okay? Every input of size n is equally likely. That kind of thing. But there are other ways that you could make that assumption, and they may not all be true. So this is much more complicated, as you can see. Fortunately, all of you have a strong probability background, and so we will not have any trouble addressing these probabilistic issues of dealing with expectations and stuff. Okay? So if you don't, time to go and say, gee, maybe I should take that probability class. That's a prerequisite for this class. Okay. Last one I want to mention is best case analysis. And this I claim is bogus. Bogus! No good. Why is best case analysis bogus? Yeah.
Case probably doesn't ever happen.
The best case probably doesn't ever happen. Actually, it's interesting because for the sorting problem, the most common thing that gets sorted are things that are already sorted. Interestingly. Okay, so for example, or at least almost sorted. Okay, so for example, one of the most common things that's sorted is check numbers by banks. They tend to come in the same order that they're written. Okay, so that they're sorting things that are almost always sorted. Okay, but I mean it's good, but okay, you want to.
Yeah, that's because you want an upper bound, not a lower bound, really.
An upper bound, not a lower bound.
That's going to make a guarantee. But
Yeah, you want to make a guarantee, and so why is this not a guarantee?
it's
Is it?
not guaranteed that you're going to get something that's like the best case.
Okay, so I mean you're onto something there. You're onto something, but we need a little more precision here. Okay, how can I cheat? Yeah.
You can check for specific inputs and just have it return
Yeah, you can cheat. Okay, you cheat with it. You take any slow algorithm you want and just check for some particular input, and if it's that input, you say immediately, yeah, okay, here's the answer. And it's got a good best case, but it doesn't tell you anything about the vast majority of what's going on. Okay, so you can cheat. Okay, with a slow algorithm that works fast on some input. Doesn't really do much for you. Okay, so we normally don't worry about that. Okay, so let's see. What is insertion sort's worst case time? Okay, so now we get into some sort of funny issues. First of all, it depends on the computer you're running on. Whose computer? Right? Is it a big supercomputer, or is it your wristwatch? Okay, they have different computational abilities. Okay? And when we compare algorithms, we compare them typically for relative speed. Okay? This is if you compared two algorithms on the same machine. You could argue, well, it doesn't really matter what the machine is because I'll just look at their relative speed. But of course, I may also be interested in absolute speed. Is one algorithm actually better no matter what machine it's run on? And so this kind of gets sort of confusing as to how I can talk about the worst case time of an algorithm, a piece of software, when I'm not talking about the hardware. Okay? Because clearly if I run on a faster machine, my algorithms are going to go faster. So this is where you get the big idea of algorithms, which is why algorithms is such a huge field, why it spawns companies like Google, like Akamai, like Amazon, okay? Why algorithmic analysis has been such, throughout the history of computing, has been such a huge success, is our ability to master and to be able to take what's apparently a really messy, complicated situation and reduce it to being able to do some mathematics. Okay? And that idea is called asymptotic analysis. And the basic idea of asymptotic analysis is to ignore machine-dependent constants and look, instead of at the actual running time, look at the growth of the running time. Oops. Okay. Okay, so we don't look at the actual running time, we look at the growth. Okay, so let's see what we mean by that. So this is a huge idea. It's not a hard idea, otherwise I wouldn't be able to teach it in the first lecture. But it's a huge idea. We're going to spend a couple of lectures understanding the implications of that, and we'll basically be doing it throughout the term. And you will, if you go on to be practicing engineers, you'll be doing it all the time. In order to that, we adopt some notations that are going to help us. And in particular, we adopt asymptotic notation. Okay? So most of you have seen some kind of asymptotic notation. Maybe a few of you haven't, but mostly you should have seen a little bit. The one we're going to be using in this class predominantly is theta notation. Okay? And theta notation is pretty easy notation to master, because all you do is you just, from a formula, you just drop low-order terms and ignore leading constants. Okay? So for example, if I have a formula like 3n cubed plus 90n squared minus 5n plus 6046, I say, well, what lower order terms do I drop? Well, n cubed is a bigger term than n squared. So I'm going to drop all these terms, and I'm going to ignore the leading constant. So I say that's theta of n cubed. That's pretty easy. Okay? So that's theta notation. Now this is an engineering way of manipulating theta notation. There's actually a mathematical definition for this, which we're going to talk about next time, okay? Which is a definition in terms of sets of functions. And you are going to be responsible in this class. This is both a math and an engineering, computer science engineering class. So throughout the course, you're going to be responsible both for mathematical rigor, as if it were a math course, and engineering common sense, because it's an engineering course. Okay, we're going to be doing both. Okay? So this is the engineering way of understanding what you do. So you're responsible for being able to do these manipulations. You're also going to be responsible for understanding the mathematical definition of theta notation and of its related O notation and omega notation. Okay? So if I take a look as n approaches infinity, a theta n squared algorithm always beats, eventually, a theta of n cubed algorithm. As n gets bigger, doesn't matter what these other terms were if I were describing the absolute precise behavior in terms of a formula. Okay? If I had a theta n squared algorithm, it would always be faster for sufficiently large n than a theta n cubed algorithm. Wouldn't matter what those low order terms were. Wouldn't matter what the leading constant was. Okay? This one will always be faster. Even if you ran the theta n squared algorithm on a slow computer and the theta n cubed algorithm on a fast computer. So the great thing about asymptotic notation is it satisfies our issue of being able to compare both relative and absolute speed. Okay? Because we're able to do this no matter what the computer, no matter what the platform. So on different platforms, we may get different constants here, machine-dependent constants for the actual running time. But if I look at the growth as the size of the input gets larger, the asymptotics generally won't change. Okay? So for example, I just draw that as a picture. So if I have n on this axis and t of n on this axis, then this may be this may be, for example, a theta n cubed algorithm, and this may be a theta n squared algorithm. There's always going to be some point, n naught, where if you go for everything larger, the theta n squared algorithm is going to be cheaper than the theta n cubed algorithm, no matter how much advantage you give it at the beginning in terms of the speed of the computer you're running on. Now, from an engineering point of view, there's some issues we have to deal with, because sometimes it could be that that n0 is so large that, you know, the computers aren't big enough to run the problem. So that's why we nevertheless are interested in some of the slower algorithms. Okay, because some of the slower algorithms, even though they may not asymptotically be slower, I mean, asymptotically they'll be slower, they may still be faster on reasonable sizes of things. And so we have to both balance our mathematical understanding with our engineering common sense in order to do good programming. So just having done analysis of algorithms doesn't automatically make you a good programmer. Okay? You also need to learn how to program and use these tools in practice to understand when they're relevant and when they're not relevant. Okay? So there's a saying that if you want to be a good programmer, you just program every day for 2 years, you'll be an excellent programmer. Okay? If you want to be a world-class programmer, you can program every day for 10 years. Or you can program every day for 2 years and take an algorithms class. Okay? Okay, so let's get back to what we were doing, which is analyzing insertion sort. So we're going to look at the worst case. Which, as we mentioned before, is when the input is reverse sorted. So the biggest element comes first and the smallest last. Because now every time you do the insertion, you've got to shuffle everything over. Okay? So you can write down the running time by looking at the nesting of loops. So what we do is we sum up. So what we assume is that every operation, every elemental operation, is going to take some constant amount of time. But we don't have to worry about what that constant is, because we're going to be doing asymptotic analysis. As I say, it's the beauty of the method is that it causes all these things that are real distinctions to sort of vanish. We sort of look at them from 30,000 feet rather than from 3 millimeters or something. Okay. So each of these operations is going to sort of be a basic operation. One way to think about this in terms of counting operations is counting memory references. How many times do you actually access some variable? Okay, that's another way of sort of thinking about this model. So when we do that, well, we're going to go through this loop. J is going from 2 to n, okay, and then we're going to add up the work that we do within the loop. So we can sort of write that in math as summation of j equals 2 to n. Okay? And then what is the work that's going on in this loop? Well, the work that's going on in this loop varies. But in the worst case, how many operations are going on here for each value of j? So for a given value of j, how much work goes on in this loop? Somebody tell me asymptotically. Yeah, asymptotically is, so it's j times some constant, so it's theta j. Okay, so there's theta j work going on here because this loop, okay, starts out with I being j minus 1, and then it's doing just a constant amount of stuff for each step of the value of I, and I is running from j minus 1 down to 0. So we can say that that's theta j work that's going on. People follow that? Okay. And now we have a formula we can evaluate. So what is the evaluation? If I want to simplify this formula, what's that equal to? Sorry, in the back there? Yep, okay. So that's just theta n squared. Good. Okay, because this, when you're saying it's the sum of consecutive numbers, you mean what? What's the mathematical term we have for that? So we can communicate. Got to know these things so you communicate. It's called what type of sequence? It's actually a series, but that's okay. What type of series is this called? Arithmetic series. Good. Wow. Got some sharp people who can communicate. Okay, this is an arithmetic series. You're basically summing 1 plus 2 plus 3 plus 4. Some constants in there, but basically it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 up to n. That's theta of n squared. Okay? So if you don't know this math, there's a chapter in the book, or you could have taken the prerequisite. Okay? Right? Arithmetic series, people have this vague recollection. Oh, yeah. Okay, good. Now, you have to learn these manipulations. We'll talk about it a bit next time. Okay? But you have to learn your theta manipulations for what works with theta. You have to be very careful because theta is a weak notation. Okay? So strong notation is something like Leibniz notation from calculus, where the chain rule is just canceling two things, and just it's fabulous that you can cancel in the chain rule. Okay, and Leibniz notation just expresses that so directly you can manipulate. Theta notation isn't like that. If you think it's like that, you're in trouble. You really have to think of what's going on under the theta notation, and it's more of a descriptive notation than it is a manipulative notation. There are manipulations you can do with it, but unless you understand what's really going on under the theta notation, you will find yourself in trouble. Okay? And next time we'll talk a little bit more about theta notation. So is insertion sort fast? Well, it turns out for small n, it's moderately fast. Okay, but it is not at all for large n. Okay. So I'm going to give you an algorithm that's faster. It's called merge sort. I wonder if I should leave insertion sort up. Why not? Okay. I'm going to write on this later. Okay, so if you're taking notes, leave some space on the left. So here's merge sort of an array A from 1 up to n. And it's basically 3 steps. If n equals 1, we're done. Sorting one element, it's already sorted. All right, okay. So recursive algorithm. Otherwise, what we do is we recursively sort A from 1 up to the ceiling of n over 2, and the array A of the ceiling of n over 2 plus 1 up to n. Okay, so we sort 2 halves of the input. And then 3, we take those 2 lists that we've done and we merge them. And to do that, we use a merge subroutine, which I'll show you. So the key subroutine here is merge. And it works like this. I have two lists. Let's say one of them is 20. I'm doing this in reverse order, 7, 2. So I've sorted this like this. And then I sort another one. I don't know why I do it this order, but anyway. Okay. And here's my other list. I have my two lists that I've sorted. So this is A1 up to A ceiling of n over 2, and ceiling of n over 2 plus 1 up to AN for the way it will be called in this program. Okay. And now to merge these two, what I want to do is produce a sorted list out of both of them. So what I do is that first observe where is the smallest element of any two lists that are already sorted. It's in one of two places, the head of the first list or the head of the second list. So I look at those two elements and I say, which one is smaller? This one is smaller. So then what I do is I output into my output array the smaller of the two, and I cross it off. And now where's the next smallest element? And the answer is it's going to be the head of one of these two lists. So then I cross out this guy, put him here, and circle this one. And now I look at these two guys. This one's smaller, so I output that and circle that one. Now I look at these two guys, output 9. So every step here is some fixed number of operations that's independent of the size of the arrays at each step. Okay? Each individual step is just me looking at two elements and picking out the smallest and advancing some pointers into the array so that I know where the current head of that list is. Okay? And so therefore the time is order n on n total elements. So the time to actually go through this and merge two lists is order n. We sometimes call this linear time. Okay? Because it's not quadratic or whatever. It's proportional to n. Okay? Proportional to the input size. So it's linear time. I go through and I just do this simple operation, just working up these lists, and in the end I've done essentially n operations, order n operations, each of which costs constant time. That's a total of order n time. Okay? Everybody with me? Okay. So, so this is a recursive program. We can actually now write what's called a recurrence for this program. And the way we do that is we say, let's let the time to sort n elements be t of n. Then how long does it take to do step 1? That's just constant time. Okay, we just check to see if n is 1, and if it is, we return. So that's independent of the size of anything that we're doing. It just takes a certain number of machine instructions on whatever machine, okay, and we say it's constant time. So we call that theta 1. This is actually a little bit of an abuse, okay, which if you get into it, then the reason is because typically in order to say it, you need to say what it's growing with, and nevertheless we use this as an abuse of the notation just to mean it's a constant. Okay? So that's an abuse. Just so people know. Okay? But it simplifies things if I can just write theta 1, and it basically means the same thing. Okay? Now we recursively sort these two things. So how can I describe that? If I'm going to recur the time to do this, I can describe as recursively as t of ceiling of n over 2 plus t of n minus ceiling of n over 2. That's actually kind of messy, so what we'll do is we'll just be sloppy. Write t of n over 2, 2t of n over 2. Okay, so this is just us being sloppy. And we'll see on Friday in recitation, it's okay to be sloppy. Okay, that's the great thing about algorithms, is you can, as long as you're rigorous and precise, you can be as sloppy as you want. Okay? Okay, so this is sloppy because I didn't worry about what was going on, because it turns out it doesn't make any difference. And we're going to actually see that that's the case. And finally, I have to merge the two sorted lists, which have a total of n elements, and we just analyze that using the merge subroutine. That takes us theta n time. So that allows us now to write a recurrence for the performance of merge sort. Let's just say that T of n is equal to theta 1 if n equals 1, and 2 T of n over 2 plus theta of n if n is bigger than 1. Okay? Because either I'm doing step 1 or I'm doing all steps 1, 2, and 3. Then I'm doing step 1 and I return and I'm done, or else I'm doing step 1, I don't return, and then I also do steps 2 and 3. So I add those together. I could say theta n plus theta 1, but theta n plus theta 1 is just theta n, because theta 1 is a lower order term than theta n. I can throw it away. Okay? So it's either theta 1 or it's 2 T of n over 2 plus theta n. Okay? Now typically we won't be writing this. Usually we omit this if it makes no difference to the solution of the recurrence. We'll usually omit constant base cases, because in algorithms, it's not true generally in mathematics, but in algorithms, if you're running something on a constant size input, it takes constant time, always. Okay, so we don't worry about what this value is, and it turns out it has no real impact on the asymptotic solution of the recurrence. So how do we solve a recurrence like this? I now have T of n expressed in terms of T of n over 2. Okay? So that's what we're going to do in, so that's in the book, and it's also in lecture 2. So we're going to do lecture 2, okay, to solve that. But in the meantime, what I'm going to do is give you a visual way of understanding what this costs, which is one of the techniques we'll elaborate on next time. It's called a recursion tree technique. And I'll use it for the recurrence that's almost the same, 2t of n over 2. But I'm going to actually explicitly, because I want you to see where it occurs, plus some constant times n, where c is a constant greater than 0. So we're going to look at this recurrence, okay, with a base case of order 1. Okay, so I'm just making the constant in here, the upper bound on the constant, be explicit rather than implicit. Okay? And the way you do a recursion tree is the following. You start out by writing down the left-hand side of the recurrence. And then what you do is you say, well, that's equal to, and now let's write it as a tree. I do C of n work, plus now I'm going to have to do work on each of my two children, T of n over 2 and T of n over 2. So if I sum up what's in here, I get this, because that's what the recurrence says. T of n is 2t of n over 2 plus cn. I have 2t of n over 2 plus a cn. Then I do it again. I say you have cn here. I now have here cn over 2, and here cn over 2. And each of these now has a t of n over 4. And these each have a t of n over 4. And this has a t of n over 4. And I keep doing that. The dangerous dots. Okay. And if I keep doing that, I end up with it looking like this. And I keep going down till I get to a leaf. And a leaf, I have essentially a t of 1. That's theta 1. Okay, or a t of... And so the first question I ask here is, what is the height of this tree? Yeah. Yeah, it's log n. It's actually very close to exactly log n, because I'm starting out with, at the top, with n, and then I go to n over 2 and n over 4 and over all the way down till I get to 1. So the number of halvings of n till I get to 1 is log n. So the height here is log n. Okay? It's okay if it's constant times log n, but it doesn't matter. Okay? How many leaves are in this tree, by the way? How many leaves does this tree have? Yeah. Yeah, so the number of leaves is actually, once again, it's actually pretty close. It's actually n. Okay, if you took it all the way down. If you've made simplest, let's make some simplifying assumption. N is a perfect power of 2. Okay, so it's an integer power of 2. Then this is exactly log n to get down to t of 1, and then there are exactly n leaves. Okay, because the number of leaves at the first here is, the number of nodes at this level is 1, 2, 4, 8, and if I in general go down height h, I have 2 to the h leaves. 2 to the log n, that's just n. Okay? Okay, so we're doing math here, right? Okay. So now let's do figure out how much work. If I look at adding up everything in this tree, I'm going to get t of n. So let's add that up. Well, let's add it up level by level. How much do we have in the first level? Just Cn. If I add up the second level, how much do I have? Cn. How about if I add up the third level? Cn. How about if I add up all the leaves? It's theta n. Okay. It's actually not necessarily Cn because the boundary case may have a different constant. Okay. So it's actually theta n. But Cn all the way here. So if I add up the total amount, that's equal to Cn times log n, because that's the height. That's how many Cn's I have here, plus theta n. And this is a higher order term than this, so this goes away. Get rid of the constants. That's equal to theta of n log n. Okay? And theta of n log n is asymptotically faster than theta n squared. So merge sort on a large enough input size is going to beat insertion sort. Okay? Merge sort is going to be a faster algorithm. Sorry, you guys, I didn't realize you couldn't see over there. Okay? Should speak up if you can't see. Okay? So this is a faster algorithm because theta n log n grows more slowly than theta n squared. And merge sort asymptotically beats insertion sort. So even if you ran insertion sort on a supercomputer, somebody running on a PC with merge sort for sufficiently large input, clobber them. Okay, because actually n squared is way bigger than n log n once you get the n's to be large. Okay? And in practice, merge sort tends to win here for n bigger than, say, 30 or so. So if you have a very small input, like 30 elements, insertion sort is a perfectly decent sort to use. Okay? But merge sort is going to be a lot faster even for something that's, only a few dozen elements. Okay? It's It's going to actually be a faster algorithm. Okay? So that's sort of the lessons, okay? So remember that to get your recitation assignments and attend recitation on Friday, because we're going to be going through a bunch of the things that I've left on the table here. And see you next Monday.